Greetings and welcome to the first lecture on unit number 3, that is fluid kinematics. We have discussed in the introductory sessions that fluid mechanics is mainly divided into three sub-branches. Fluid statics, where we study the behavior of fluid when it is at rest. Fluid kinematics, where we study the motion of the fluid without considering the forces causing the motion. In dynamics, we consider the uh, forces causing the motion as well. So in fluid kinematics, we are dealing with only a flow parameters, that is the velocity, acceleration, and other hydrodynamic parameters. This session, we are going to discuss the flow description methods. So there are different approaches used for the analysis of the flow, or to define or to describe the flow field. There are two approaches that can be used: the Lagrangian approach and Eulerian approach. Lagrangian approach, velocity and other hydrodynamic parameters like density, pressure are specified for a particular particle. And this approach is most suitable and widely used for particle and solid mechanics. While in Eulerian approach, the velocity and other hydrodynamic parameters are expressed as a function of location and time. Analysis is performed by defining a control volume to represent a fluid domain, which allows the fluid to flow across that particular control volume. And this approach is more appropriate to be used in fluid mechanics. In other words, the Lagrangian approach is also called as a particle approach, where a particular particle is monitored and its behavior is observed. Generally, the scientists use this particular approach, and it is mainly applicable for the situation where the gas density is very low, especially in space situation where there is no contact between two fluid particles. So individual fluid particle need to be studied. Eulerian approach, it is also called as a field approach. This generally engineers use this particular approach. In our fluid mechanics also, we are going to use the same approach as well, where a particular flow domain is monitored and the particle passing through that, the behavior of particles passing through that particular flow domain is monitored with respect to time as well as with respect to location. So this is a pictorial demonstration of the two approaches. Mr. Euler, he follows the Eulerian approach. Mr. Lagrange, he follows the Lagrangian approach. Mr. Euler is standing on the bridge and is monitoring the temperature of the fluid at that particular domain, so near the bridge only. While Mr. Lagrange is monitoring the temperature of the fluid while traveling with the boat. So maybe he's traveling with the flow and is monitoring the temperature of the same flow or same fluid particles. He observed, Mr. Euler, he observed in 1 hour, he observed there is 2-degree temperature rise, while Mr. Lagrange, he observed there is a drop in 1-degree temperature per hour. So obviously there, because of the differences in approaches, Mr. Euler is he's monitoring the temperature of the fluid passing through this domain only. And within 1 hour, he observed there is a 2-degree rise. While Mr. Lagrange is traveling with the boat, and maybe he's traveling with the same flow or same fluid particles, and he has monitored the temperature of that fluid particle 1 hour before, and he found after 1 hour that there is 1-degree drop in temperature. So that is the difference between Lagrangian approach and Eulerian approach, where this approach is called as a particle approach, or is traveling along with the flow. And this approach is called as a field approach because it's monitoring the flow only in this particular vicinity. So whatever the parametric changes happening is monitoring and recorded. So these are the two approaches generally used. And these two approaches are used for calculating the velocities and acceleration. Now, first of all, we'll see how to calculate the velocity and acceleration of fluid particle using a Lagrangian approach. In this method, the observer concentrates on the movement of a single particle, the path taken by the particles, and the changes in its velocity and accelerations are studied. In Cartesian system, suppose the position of the fluid particle in space at one particular time t is x, y, z from its original position, that is x naught, y naught, and z naught at time t is equal to 0. So it can be represented that x is a function of its original position and time, y is also a function of its original space coordinates and time, and z is also a function of its original space coordinate and time. Then the velocity and acceleration components obtained by taking derivative of all these space coordinates with respect to time. So we have x component velocity is dA by x by dA by t. Y component velocity v is dA by y by dA by t, and w component is dA by z by dA by t. Similarly, the acceleration is the double derivative of u. In fact, dA by u by dA by t is acceleration with respect to time. So u is dA by x by dA by t. So acceleration along x direction is dA by 2x by dA by t square. Acceleration along y direction is dA by 2y by dA by t square. Acceleration along z direction is dA by 2z by dA by t square. So this way, and these are the velocities and acceleration of a particular fluid particle. So if there are n number of particles, so every particle is monitored and the velocities and accelerations are determined. At any point, the resultant velocity vector is obtained. Again, this is the resultant velocity of a particular particle under root u square plus v square plus w square, or acceleration is under root ax square plus ay square plus az square. So this way, in Lagrangian approach, the resultant velocity and accelerations are determined for a particular particle. Similarly, other quantities like pressure densities are can also be found out. While in Eulerian approach, the observer concentrate on a point in a fluid system. The velocity, acceleration, and other characteristics of the fluid at that particular point are studied. So this method is almost exclusively used in fluid mechanics, especially because of its mathematical simplicity. In fluid mechanics, we are not concentrated with the motion of each particles, because in fluid mechanics, the particles are moving in assemblage of particles. So there are continuity of the particle movement. So that's why only a domain is monitored. But we study the general state of the motion at various points in the fluid system. So the velocities at any point, we can say x, y, z, can be determined as that particular point is velocity component. These are the x, y, and z component of velocity. And all these components are the function of space coordinate x, y, z, and t. The component of acceleration of the fluid particle can be worked out according to the chain rule or by partial differentiation as follows. So if we differentiate this with, because the u varies with x, y, z, and t. So differentiating u with respect to x, y, and z, we get. So du is equal to dA by u by dA by x into dx plus dA by u by dA by y into dy plus dA by u by dA by z into dz plus dA by u by dA by t into dt. Because u varies with all space coordinates, so the variation of the velocity with respect to each coordinate is determined, and with respect to time as well. So if we divide both sides by time, dt, then we have this expression. So divide both sides by t. But in this expression, dx by dt is nothing but velocity along x direction at that particular point. Similarly, dy by dt is the velocity with respect to y, that is y component velocity. And dz by dt is the velocity with respect to z, that is z component velocity dt. So by putting, instead of dx, dy, dz, if we put vw, so we get this expression, that is x, because du by dt, that is d is used for the total derivative, because acceleration, it varies with respect to space coordinate as well as it varies with the time as well. So this is acceleration along x direction, or we can say that u into dabba u by dabba x plus v into dabba u by dabba y plus w into dabba u by dabba z plus dabba u by dabba t. Similarly, the acceleration along y and z directions are obtained like this. So here the acceleration is a function of velocity. Velocity at the one particular point is monitored, and the acceleration with respect to that particular field is obtained. So these are the three components of accelerations. Its resultant velocity and acceleration at any point shall be obtained by using resultant velocity v is equal to under root u square plus v square plus w square. In similar way, but here the velocity and accelerations are monitored or measured at one particular point. So not one particular particle. That is the difference. So the velocity vector, that is called as a velocity field, we can say, because this is a field approach, the vector quantity is used. So the velocity, which is a directional quantity. So velocity vector is given by v bar, that is equal to u into I hat plus v into j hat plus w into k hat. Similarly, the acceleration vector a bar, that is equal to ax into I hat plus ay into j hat plus az into k hat. So this way, we can calculate the velocity and acceleration in both approaches, that is Lagrangian approach and Eulerian approach. The difference is that in Lagrangian approach, we have estimated velocity and acceleration for a particular particle. And in Eulerian approach, we have estimated the velocity and acceleration at a particular point. Now we'll discuss the concept of total or material or substantial derivative. Now we have acceleration along x direction. We already determined previous slide. That is x direction acceleration, which is also given by du by dt. So capital D is used because it is a total derivative. It is a total acceleration, you can say, because it's acceleration addition of all accelerations, you can say. So this is the expression what we had derived in previous slide, that is u into, that is acceleration along x direction. All the x component velocities are used and their variation along x, y, and z directions. Then the same expression can be used for any field. So any field we can consider as any parameter, flow parameter or hydrodynamic parameter, that is eta. So the same expression we can use for eta. So u is replaced by eta everywhere because u is only common here. For ay, u is replaced by v. So only u is the variable along x direction. So dabba eta by dabba t, that is equal to this field. Only u is replaced by eta. So in conservative form, we can replace this eta with respect to this field. This is a conservative form of differentiation. On a vector form we can write. So d eta by dt, that is equal to dabba eta by dabba t. And instead of this term, it is a product of two vectors, because product of two vectors is also a scalar quantity. So if we see the velocity vector v is u into I hat plus v into j hat plus w into k hat, and the gradient field of eta, it is again gradient eta is a vector field. So we can write this, and if you take the product of these two, it is this only. That is u into dabba eta by dabba x, v into dabba eta by dabba y, and w into dabba eta by dabba z. So instead of this term, we can put product of two vectors, that is v bar into del eta. So del is called known as a gradient operator. So this is a conservative form of a total rate of change for any field eta. So the operator of this total derivative, so this d by dt is called as the total derivative. So beta is a variable. So the operator is this, that is d by dt, that is equal to dabba by dabba t plus v bar into del. So this is a operator for total derivative. So generally, these conservative forms we generally require for programming while coding, because coding generally these conservative forms are used, especially in CFD, that is computational fluid mechanics. When for computational analysis, this coding is required, and for the coding, these conservative forms are used. So this is a conservative form, or this is, we can say, the operator of total derivatives. So if this operator is used for velocity, we can put it the velocity. If this operator is used for any other parameter like pressure, we can place pressure only here. And accordingly, the derivatives are taken. So this d by dt, that is called as material or substantial or total rate of change, while dabba by dabba t, that is called as a local rate of change at a given spatial locations, and the combined term v bar dot del, that is called as a convective rate of change. So consequently, the total or substantial or material rate of change is the addition of local rate of change plus convective rate of change. So this is called as a total or material or substantial derivative. So this concept is used for estimating the variation of any flow field like velocity, pressure, density, or any other hydrodynamic parameter. The same operator is used. The variation we can analyze. Now, for example, the variation of velocity, we have operator from the operator we can obtain. This is operator for total derivative. So eta is for velocity field, eta is replaced by v bar, that is a total velocity vector. That is d v bar by dt, that is equal to dabba v bar by dabba t plus v bar into del v bar. So this is a velocity vector. In non-conservative form, because this velocity vector has three components, the component along x direction, y direction, and z direction. So the rate of change of velocity, this is called as acceleration. So the acceleration along x, y, and z direction, we can write in non-conservative form. So instead of the v bar, we can replace v bar into a small u in order to calculate acceleration along x direction. This is non-conservative form. Instead of this, we can write in scalar form, that is, instead of v bar, that is u v w, or u into I hat plus v into j hat plus w into k hat. This is one vector v bar. And another vector, that is a uh, gradient field of velocity. So for x direction velocity, we can replace this del v bar in del u. And del u is nothing but that is a vector, that is dabba u by dabba x into I hat plus dabba u by dabba y into j hat plus dabba u by dabba z into k hat. So this is a acceleration vector. So this part is a convective acceleration, and this part is a local acceleration. Similarly, the acceleration vector, acceleration along y direction is given by this expression, and acceleration along z direction is given by this expression. So this yellow terms, all these terms, they are called as a convective acceleration, the component of convective acceleration. This is called as a convective rate of change of velocity, the convective acceleration. And all these components, they are called as a local rate of change or local acceleration or local rate of change of velocity. So convective acceleration, they are generally varies with space coordinates for a particular given time. And local acceleration at one particular location, it varies with the time. So the total acceleration is addition of the convective acceleration and local acceleration. So this is about the total or material or substantial rate of change of the velocity or acceleration component. So this is about the local and the expression of total or material or substantial derivative. At the end of this particular session, you could be able to explain the two approaches of flow field, that is Lagrangian approach and Eulerian approach. and their important features when they are used. Then you could be able to determine the velocity and acceleration of flow field using a Eulerian approach. Already we have discussed if any flow field is given. So in terms of any flow field is generally given in terms of velocity vector. In that case, with the help of that, we can calculate the resultant velocity and the acceleration as well. Acceleration components and acceleration result and acceleration vector, and its representation of vector field. So easily you can derive by using the concept of the Eulerian approach. After this session, we could be able to derive an expression of total derivative of flow parameters and their uh, concepts or their importance, how the total, what is meant by the total derivative, or why the capital D later is used for the total derivative, because it is the total of convective and local acceleration. So this is the basics of fluid kinematics, where we have discussed how to calculate the velocity and acceleration in both approaches, but generally uh, we have to take away only the Eulerian approach during the course of this particular fluid mechanics. In next lecture, we will discuss the numerical part to calculate the velocity and acceleration, or the different types of flows related with the. Uh, with this, we have completed this particular session.